Right, when we look at the physical layer, as you recall, it's the circuit that makes up the first part of the OSI model, or layer one, and it's also layer one of the internet model. There's a focus on transmission over circuits, and there's the types of circuits are physical or logical. So a physical circuit includes the actual hard wires that go into the backs of the machines and connect the devices together. Logical circuits refer to the transmission characteristics of the circuit. For example, when you hear somebody say, this company has a T1 connection, or this connection is an ISDN line, or something to that effect, that is a logical example of a circuit. Thank you. When discussing circuits, there are two different primary circuit configurations, point-to-point and multi-point. Point-to-point circuits include most wired connections today, so that involves the physical wire, the Ethernet wire, the switching going, say, from one server to a client machine. That's a point-to-point circuit. Multi-point circuits are most commonly wireless connections, where there's multiple access points to the same circuit. They're also known as shared circuits, and since there's no physical setup involved, they're generally less expensive. Thank you.
All right, now let's talk about data flow. A simplex data flow moves in one direction, so communication can only happen going one way. In the example on the screen, it's from a client computer to a server. Simplex could also go from the server to the client machine, but only from the server to the client machine. That's an example of simplex. A half duplex data flow allows data to flow in two directions, but only one at a time. So in other words, you can't transmit and receive at the same time. In a half duplex situation, you can transmit or you can receive, depending on whether you're on the server side or the client side. A full duplex, which are most common today, allow simultaneous data flows in both directions, meaning that there's a connection wire for both a transmit and a receive, so they're allowed to exist at the same time. Thank you.
Now we'll discuss multiplexing. So first thing we need to do is understand what multiplexing is. Multiplexing is the idea of breaking down a high-speed physical connection into multiple lower-speed physical connections. So there's several ways that can be done. Usually there's a cost advantage. T1 lines really represent multiple voice channels, and therefore a lot of phone technologies use multiplexing, and most offices and their voice systems are based on multiplexers. Categories of multiplexing involve frequency, wavelength, and also time. Thank you. Frequency division multiplexing, or FDM, involves the horizontal multiplexing method. In other words, channels are created along the wire where traffic can be transmitted. Usually it goes in patterns of 4, which is why a T1 is represented by 24 voice channels. It's an example of an FDM. In between these channels, there's what they would really call padding. So in other words, you don't want the data to conflict with each other being sent on the different channels, so guard bands are put in place to pad the channels from each other. Thank you. Now we'll discuss WDM, or wavelength division multiplexing. It's a variant of FDM, but rather than being used on physical wire, it's used with fiber optic circuits. It makes the use of multiple wavelengths or colors to divide circuits into channels. So if we look at the rainbow below, red would represent a channel, purple would represent a channel, yellow, etc. Dense WDM can divide a circuit into more than 100 channels per fiber because there's many different colors that can be used, and each would transmit at 10 gigabits per second. So much more technology involved when using wavelength division multiplexing. Thank you. Now we'll discuss time division multiplexing, or TDM. You can look at this as not a vertical, but a horizontal method of transmission, where circuits are divided by taking their turn. In other words, one packet of information will be sent for one machine, one packet will be sent for another. So in traditional TDM, all have equal turns, meaning it's really a round robin sharing, and it's more efficient than FDM, but there'll be a lot of idle spots in there where time can be wasted. So in a busy environment, time division can be very helpful and useful. Thank you. Now we'll go in and we'll discuss a little bit more on statistical time division multiplexing, or STDM. This scares me a little bit because statistics aren't always right. Sometimes different loads and different types of traffic will be involved, and sometimes the slowdown can happen and it really can backlog things. So it's really a more specific and more calculated type of time division multiplexing, but it does create some risk. Thank you.
The diagram below provides an example of time division multiplexing. Notice that the times allocated slots are vertical as opposed to horizontal. There's nothing that resembles guard bands or anything like that. It's literally slicing up the time and dividing it amongst the different clients, and it goes through the multiplexing and demultiplexing process. So again, this is very different from FDM, and notice that packets will be sent 4321, 4321, 4321, depending on which client we're talking about and which client on this side we're talking about, or which server on this side. Thank you.
Now let's talk about media. It is the physical matter or physical objects that are used to carry voice or data transmissions. So it's your wires, it's your physical devices, your switches. That's the physical matter that makes up media. Guided media involves transmission flowing along physical medium, in other words, the actual cabling, whereas radiated media, or wireless, the transmission will flow through the air, and that's how the physical circuit is completed and made. So understand the difference between guided media and radiated media. Thank you. Right now we'll discuss the various types of guided media. The most common is the twisted pair cable. This is in most of your business workplaces. It's the actual wire that makes up your Ethernet wire. And twisted pair cable involves insulated pairs of wires bundled together. They're twisted to reduce the electromagnetic interference. Sometimes they use additional shielding, and they're commonly used, like I said, in office places. They're used with telephones, they're used with LANs. Telephone wire is also twisted pair, it just doesn't have as many wires. Currently, we use Cat6E for our Ethernet wires as our twisted pair. This book will refer to Cat5 in a lot of different places. Really, the newer standard is Cat6. So I want to make that clear. The characteristics for twisted pair cable are it's very inexpensive. It carries up a distance of up to 100 meters before repeaters or other switching devices are required. And they're used in networks, and they're used with telephones. Like I said, most office places are twisted pair going into your desktop computer that you use every day. This classroom is definitely using twisted pair. Thank you. Now we'll talk about coax. And really, when you got your old VCR, it probably came with a patch cable that was a piece of coax. That was DB56. That's not as reliable. it's much more prone to interference than the DB6 wire, which is really the cable wire that you see out on the phone lines and being directed into your house. It's what the cable companies install. The coax cable has a single copper core plus outer shielding and inner insulation. Therefore, they're much less prone to interference. Even the DB56 wires are less prone to interference. They're still inexpensive, but they're more costly than twisted pair wire because they're a lot more heavy duty, and they carry distances of up to 2 kilometers. And like I said before, they are used primarily with cable television and cable internet connections. Thank you. Next, we'll discuss the fiber optic cable. Fiber optic cable has an optical core made of glass or plastic, data transmitted using light from lasers or LEDs. It's resistant to interference and corrosion. They have very fast data rates since light is involved, and they're also very expensive. They have a good distance range of 500 meters to 1,000 or 100 kilometers. And their use is for trunk lines, backbones, long distance circuits. You might think of the undersea cables that we have. Those are fiber optic. Thank you. Now let's talk about radio. It involves the wireless transmission of electrical currents through the air, and each device on the network has a radio transceiver operating at a specific range, meaning the message is being sent out at a certain range and it's being picked up. I'm thinking by the cell phone towers. That's the great types of radio that they're really referring to here. They're referring to wireless networks. And if you actually go in and look at your wireless connection, you can see the frequency that it's broadcasting at. It actually tells you when you look at your cable modem wireless setup or on your router's wireless setup. You can actually see the frequency, and you can actually set the frequency. It enables mobile communication, and it can carry a good degree of distance depending on frequency and power. As many of you know, maybe from your car's radio, that your AM radio stations often transmit a lot further than the FM stations, and that's because AM radio transfers information based on the amplitude of the wave, where FM goes by the frequency, which puts things more bunched up and closer together. Not an important concept, but I thought I would mention that. Thank you.
We're now going to talk about microwave communication. Microwave communication can be also known as line-of-sight communication. Usually microwaves require large antennas or towers, and it uses a very high-frequency radio signal. Because of this, weather can have a tremendous impact, whether it be humidity, low cloud cover, and what have you. The distance characteristics are limited to about 60 kilometers, and that's because, believe it or not, the Earth is round. So you lose line of sight with the curvature of the Earth. And its use is for trunk lines and for long-distance backbone communication. So with a microwave transmission, it can serve as a backbone from one place to another just as long as it's line of sight. Satellite communication is a very special form of microwave communication in that, for one thing, it's a line of sight signal, but rather than have towers on the Earth, the satellite leads to outer space. And the fact that it is such a long distance can lead to delays in the propagation of data. But we all use satellite technology every day when we watch TV, and we get our communication through satellite technology very frequently. And that's about all I have to say about that slide. Thank you.
In this slide, I'd like you to look at the individual bullet points involving factors to consider in the media selection. And I'd like you to try and think of an example of a situation where you'd be setting up a network and what you'd do based on these considerations. That's the idea that needs to be followed. Is you need to think things through and plan and determine what's your best solution based on these factors. Thank you. There's a difference between digital and analog data transmission. Digital transmission involves discrete binary values such as 1 or 0, and specifically 1 or 0. When data is transmitted digitally, a 1 or a 0 will be represented and converted by the machine. Therefore, much more absolutes are determined, as opposed to analog transmission, which involves continuous waves which can be interrupted and or interfered with. You'll notice that most commonly when watching TV. When you were watching TV with analog data transmission, you could get static in your television. Once the digital cutover occurred, you'll get packet interruption occasionally. However, the picture would always be clear. That's because you're dealing in absolutes, 1s or 0s, as opposed to waves. Thank you.
All right, now let's talk about the ASCII character sets again. We briefly touched on this in Chapter 1, but I think it's worth revisiting and going into a little bit more detail. So, whoops, oh, I didn't want that to happen. Hold on. All right, so we have characters that are represented by a group of bits. So here are the group of bits that we're talking about. So how do we get A from this set of 1s and 0s here? As you know, binary values are 1s and 0s, and that's what bits are. They're single binary representations. So it's important to remember that every day when we count, when we pay bills, when we pay for gas, whatever, we're using what's called the base 10 counting system. Now, the base 10 counting system means that we work with 10 digits in our counting system. That's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's 10 digits. With binary, there's only 2 digits. And that's 0 and 1. If you've heard of hexadecimal systems, which are very common with computers, that's a 16-bit counting system. So that means there's 16 digits that we recognize. So that's base 16, hexadecimal base 16. Our regular everyday counting system is base 10, and the computer's counting system is binary, which is base 2. So that's just 0 and 1. So binary and the base 2 counting system are pretty much the same thing. On this chart here on the right, I want to show you how we derive this information here, because this can be misleading and confusing. So I'm going to step out of the slides for a second here. And I have my handy dandy Excel sheet that I've just built up here. So what you're going to do is you're going to start from the right and work left, actually. So you're going to start with 1. You're going to multiply it by 2. It's going to give you 2. In this column, you're going to multiply it by 2 again. It's going to give you 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. 32 times 2 is 64, and so on. So we talked about the extended ASCII set versus the standard ASCII set. That really is done just to eliminate this column here, just to give some additional storage. So let's take a look at the ASCII tables and let's see how we come up with this. Now in my browser, I have a better ASCII character set than I had before. Notice that everything from 128 through 255 is considered the extended character range, and it has all these clever characters like this here, which can be used with foreign languages and stuff. I know on the PC, if you wanted to bring up some of these characters in Notepad, you can hit the Alt key or hold your hand on the Alt key, then type in the numbers, say 130, and it'll give you this character right here. Going forward, though, let's look at the letter A. That is 65, and it's the letter A, as we can see here. So that's how they derive that. So let's look here. So that's 64 plus 1. So there's a 1 here. 64 plus 1 is 65. And if we go back to our slide here, whoops, hold on. If we go back to our slide here, we can see that it's set up and looks the exact same way. So now let's jump down a little bit and let's try character D. Okay, so the ASCII character for D is going to be 64 plus 4, I believe. Yes, 1, 2, 4. So 64 plus 4 is 68. So let's take a look at that one here in our picture, and we put a 0 there, and we put a 1 there, and that would represent character 68. 64 plus 4. So let's take a look at that on the actual ASCII table, and let's look at character 68. And where is 68? 68, right there, letter D. So this is a really nice diagram, actually. But that's the essentials of how we calculate the ASCII values. And when these values are transferred in serial communication, as we'll see in the next slide, it sends these individual bits. And everything that is done with computers is done in ASCII codes. There's lots and lots of different situations where the ASCII codes are important. So this is an important concept to learn. I'm probably going to make it this week's homework assignment. So that's where these characters come from, and you can test any. You can draw the simple spreadsheet picture. You can even draw it on paper to determine these different characters, and so you can look it up. For the ASCII characters that I chose, I didn't have any specific website. I just Googled ASCII characters and clicked on the first thing. And that's what you can do as well. There's tons and tons of different ASCII tables out there. You could even write a program to generate your own ASCII tables if you're programmatically inclined. But this is an important concept, and it's going to stay with you. And for a lot of the ASCII characters, I have them memorized already. For example, the carriage return and the line feed characters are something I have to work with and know about all the time, and that's carriage return is 13 and 10, respectively. So I just know that off the top of my head. You could look it up on the chart and you'd see the same thing. But these are important. I can't stress that enough. So here's an example of parallel transmission where it's transmitting all of the bits at once. So you have right here 8 bits being transmitted in parallel. Just like that. So parallel transmission is when multiple bits are transmitted simultaneously. Serial communication is when they're transferred one by one. So obviously serial communication is much simpler, but it's also much slower. So you can see you've got your binary set, your binary representation being sent, and it's sending, and you have a much wider set of packets. It's much smaller, but it's also reliable, and it's an old standard, but it's still used. So with digital transmission of digital data, the sender and the receiver must agree upon a set of symbols. How bits are encoded are voltages. So 5 volts might be encoded as 1, and 0 voltage would be encoded as 0. So thus with a digital signal, if there is voltage, it's usually a 1. If there's not, it's a 0. And there are exceptions to that, which you'll see on the next couple slides. I'm not going to go into a ton of detail on that stuff. I don't know how I can really reproduce it for this class, and it's a little bit beyond the scope of this class. So the symbol rate will tell how often the symbols are sent, and it gives you an example right here. Thank you.
For this slide and the next couple slides, we'll discuss digital transmission of digital data and how the voltage techniques are used. Just look this over. I'm not going to go into too much detail on it, and I'm not going to hold anybody to it. But get the idea of how the voltage transfers. It's interesting, and it's good to know. Thanks.
Telephone communication was originally designed for analog data. Electrical signals mimic sound waves, for example, your voice. So different pulses get sent through the wire at different frequencies to make up your actual voice reproduction on the other end. Analog transmissions take up ranges of values versus discrete values with digital transmissions. So in other words, there can be a multitude of values, which in digital transmission it's a 1 or a 0. And to convert analog data to digital data, you need to have a modulator, demodulator, or a modem to handle that conversion. Thank you.
And I would also like to add that telephone systems built for use with analog data are known as POTS line, P-O-T-S, and we're going to go into POTS lines in a few later chapters, but POTS stands for plain old telephone system. Literally, that's what it stands for. We'll go into that later.
Now we'll discuss the characteristics of waves. They have an amplitude, which is the height of the wave. As I said before, the height of the wave is what AM communicates based on. The radio signal is transmitted through airwaves using the amplitude of the wave, where FM uses the frequency. In this example, these waves are being sent through a wire, or they could be wireless as well. But amplitude is the height of the wave. The frequency of waves is the number of waves per second. It's registered in hertz. And the wavelength really is the inverse, where it just takes the length there and not the count. So the wave direction, or the point at which a wave begins, is known as the phase. Thank you. All right, so like I began to explain, the carrier wave is the basic wave transmitted through a circuit. Modulation is the modification of the carrier's wave. Some fundamental characteristics in order to encode the information and send the information. And there's 3 basic ways to modulate a carrier wave. As I've mentioned, amplitude modulation, or AM, is one example. That's AM radio, and there's several different AM radio bands. That's something you should understand as well. The range that the FCC set for our cars and for radio broadcast transmission has its specific range. Same thing with frequency modulation. And then there's PM wave, or phase modulation, which uses the phase to encode the information. Thank you.